Okay, so let's start. So in the last class, we were basically looking at the Bose-Sommerfeld formula, and as I was saying, that Sommerfeld generalized Bose quantization rule to include elliptical orbits. In other words, include angular the concept of angular momentum to whatever Bohr had considered, and so what he showed was that, like, he basically followed the idea from Kepler problem, and he wanted to see whether he can actually recover equation of an ellipse. Okay. So for that, he wrote down the spherical line element. This is something we did last time, but let me just repeat a bit. And the radial part of the equation was this. This is the kinetic part. This is centrifugal piece. This is Coulomb piece, and so on. Okay, and of course, if you have an elliptic orbit, then r is actually not an independent variable. It depends on the angle. So therefore, you can kind of trade it off r dot to dr by d omega times d omega by dt. D omega by dt, of course, is just L upon m r squared. So therefore, you can kind of replace r dot by using this relation further in this radial part of the equation. Okay. Angular momentum, of course, is written in terms of quantized rule k times h bar. So you can kind of read off omega dot from this as L upon m r squared. Okay. So now we can substitute whatever r dot we have in the equation, and we can recover this equation, which is 1 over r squared dr by d omega whole squared is equal to some quantity on the right hand side. Okay. And this equation, of course, simplifies if you write down rho is equal to 1 over r, and in terms of rho, this equation is simple because this is just d rho by d omega whole squared is equal to minus rho squared plus this quantity times rho plus 2m e upon L squared. Okay, so given that is d rho by d omega whole squared, you can get d rho by d omega by just taking square root on the right hand side. Okay, so if you integrate that, you get a solution for omega minus omega naught, and you can invert that relation to write down rho in this particular fashion. And this is what is called the equation of ellipse. And in this equation, you can write it in this particular form, and the epsilon in this case is what one calls the eccentricity. Okay, so once you get this solution, it's kind of easy to read off that A would be this quantity, mz e squared upon L squared, and epsilon would be square root of 1 plus 2L squared E upon mz squared e to the 4. Okay. Fine. So, so as I said, this is an ellipse, and we kind of identify major minor axis of this ellipse and determine that the major axis is related to z squared upon 2e with a minus sign. This thing, that minus sign just tells you that the energy is negative, and b is L upon square root of minus 2me, which is the minor axis. Okay, so let's continue kind of looking at the Bohr-Sommerfeld quantization problem. What we basically want to do is to recover the leading order hydrogen atom spectrum without actually solving Schrodinger equation, but just use Bohr-Sommerfeld quantization thing. This computation can also be done for a relativistic case. I would probably give that as a home assignment, but let's look at how we do this in the non-relativistic situation. So in the Bohr-Sommerfeld quantization rules are like this. The angular momentum quantization rule is this, which we had already encountered earlier. The theta part of the angular variable is quantized in terms of n theta. Azimuthal piece is quantized in terms of m, and the radial piece is quantized in terms of n prime. Now, one may wonder as to why I'm writing kind of contour type integral for radial variable, and the answer is that although radial variable is non-compact, This integral is not to be done in this fashion because the radial variable is actually not an independent quantity. It is a function of compact coordinates, and therefore dr could be traded off to d theta or d omega integrals, okay, which is what we will do basically. Okay, so let's consider a sphere line element with radius r, and that is given by this quantity. It's the same thing which is multiplied by r squared now, that's all. Okay, and what we want to do is multiply this by m, which is the mass of the particle, not this quantum number, I'm sorry, there's just too many m's sitting around. And look at the time variation of these infinitesimal elements. Okay, so if you do that, then you get an expression which is m r squared. You get a factor of 2 times omega dot times d omega. Similarly, you get factor of 2 from each one of them. So forget about factor of 2. And then you get this expression, which is mr squared omega dot d omega is equal to mr squared theta dot d theta plus, oh, I should have written m here also, mr squared sine squared theta phi dot d phi. Okay. And you can easily see from this that these quantities are basically mr squared omega dot is the p omega, this is p theta, and this is p phi with an m here. Okay. So okay, so we can use this, and this relation tells us basically that if you do integral of this expression, then we know the quantization rule for each one of them, and this quantization rule tell us that k is equal to n theta plus m. Okay? That is the relation between these quantities. Okay. What we actually want to do is to find how we would replace PR in the radial equation. We have a PR squared factor, how we will replace that by doing integrals over compact variables. Okay, so one way to do that is to write down PR dr is equal to PR dr by dt times dt by d omega, and times d omega, of course, and dt by d omega is something we know, and dr by dt is also something we know. We have already done this computation. Okay, so yeah, maybe I will not go back, but I had done this earlier. R dot computation. Okay, so these quantities are written out here. Okay, so using that, we could write down this expression as PR squared. Yeah, maybe. Uh, yeah. Anyway, I have written it out here so that I don't have to go back and forth. So PR, this expression therefore becomes PR squared times R squared upon P omega squared d omega. Okay. What we have done is we have used R dot, which is dr by dt, is equal to PR upon m. Okay. So that gives you PR squared by m. But then omega dot is 1 over mr squared times p omega. So therefore, since omega dot is kind of in the denominator, the mass term cancels out and you get this factor. Okay, so we get this relation, and what we want to do is to utilize these kind of relations to replace PR squared and try to write down this expression in simpler form. Okay, so of course this is the energy of the atom, because it's a kinetic piece, centrifugal piece, Coulomb piece, would add up to give you a total energy. So we replace PR squared by using this relation. So take this equation, write down PR squared in terms of energy and all other variables, and plug it into this integral that we were trying to do. Okay, integral PR dr. Okay, fine. So this is a bit of algebra, but let's kind of go through this piece. So let me do a small thing. So we want some relations, so we can, I just want to kind of keep those relations here. Okay, fine. So, oops, wrong place. Yeah. So we have an expression which looks like this. Okay, and what we want to do is to replace the quantities in terms of A and epsilon. Okay, so A and epsilon are given out here, And and 1 over r, sorry, I have to still have to kind of roll back. I'm sorry. Mm. So 1 over r is the expression that we have out here. Sorry, not here. Here. Okay. And that 1 over r is just a plus a into 1 plus epsilon sine omega. Okay. So that is the expression that we are going to substitute.